All right, good afternoon, everybody. It is Thursday here, and I am logging in to do the video. The top voted question for today was 7.4, number 10, and it's this. So let A be a non-empty set. Fix a set B, where B is a subset of A. Define the relation R on the power set by X is related to Y if B intersect X is equal to B intersect Y. First thing we have to do is verify that this is an equivalence relation. Make a bit more room here. All right, so we got three things to show. We need to show that R is reflexive, symmetric. Nope, sorry. Symmetric. That's right. Symmetric. And transitive. We need to show that it is reflexive, symmetric, and transitive to be an equivalence relation. Let's do it. So to show it is reflexive, first off, our set is P of A. So I need to pick one element in the power set, and I need to show that this element X is related to itself. Right? So I need to show X is related to X, since the definition there would be B intersect X is the same as B intersect X, which of course is true. Thus, for that arbitrary element of the power set, it's X is related to itself. Thus, everything's related to itself. So R is reflexive. If you're struggling to understand what this stuff is, it can look like I've done nothing here. Okay, but I've proven everything I need to show. So make sure you understand what's going on here. 2, I need to show it's symmetric. So I need to let X and Y be in the power set of A, be such that X is related to Y. Well, all I know is the definition of that. That is, B intersect X is the same as B intersect Y. Well, if B intersect X is the same as B intersect Y, what do I need to show now? I need to show now that Y must be related to X. But that's just saying that B intersect Y is the same as B intersect X, which is the same thing here. So that's exactly what I need to do. Since B intersect X is the same as B intersect Y, therefore B intersect Y is the same as B intersect X. It's kind of obvious, but I should say it, because then what I can conclude there, that's the definition of Y being related to X.
Hey everybody, let's take a break from the example for a sec. The example I'm doing here is really just a single example, and there are literally infinitely more problems you can run into on a discrete math exam. And odds are good you'll run into problems you've never seen before and be expected to apply what you know to solving them. But if you don't understand the content, you have no hope. So if you're taking a university, if you're a student taking a university discrete math course, and you're serious about not just getting a good grade, of course, yes, getting a good grade, but if you're serious about understanding the content, then go ahead and click the first link in the description down below and book a free call with me. Now, back to the example.
Thus, R is symmetric. 3, transitive. Let X, Y, and Z all be in the power set of A, such that X is related to Y and Y is related to Z. I now need to show that X must be related to Z. That is definition. B intersect X is the same as B intersect Y, and Y is related to Z, so B intersect Y is the same as B intersect Z. I now need to show that X is related to Z. In other words, B intersect X is the same as B intersect Z. And of course that's true. B intersect X is the same as B intersect Y, which is the same as B intersect Z. B intersect X equals B intersect Y, which is equal to B intersect Z. And so X is related to Z. Thus, R is transitive. Okay, that finishes the first part of the question. And again, just like the last video I made, this actually, having seen this now, you might be more clear on what the question is asking. So if you want to, it would not be a bad thing at all, pause the video and go try the other parts of the question now. Okay, moving on then. If A is a set 1, 2, 3, and B is a set 1, 2, find the partition of the power set of A induced by R. All right, so A, that's the original set, is at 1, 2, 3. The elements of my relation are the power set of A. In other words, all subsets of 1, 2, 3. B is this fixed set, 1, 2. And so two things are the same if and only if they have the same intersection with B. Okay, so what are the partitions? Well, there is, first off, the partition that is, let me make a bit more room here. There's the set of things that are equivalent to the empty set. Let's start there. So what is equivalent to the empty set? The empty set, if I intersect the empty set with B, I get an empty set. So the empty set is equivalent to everything else that also intersects with B and gets the empty set. Well, there's only one thing that does that. Anything, if it contains 1, then the intersection would contain 1. If it contains 2, the intersection would contain 2. But if it contains 3, and just 3, then the intersection is the empty set. And so there is one part of the partition. The empty set and the set 3 both intersect B with the same set, the empty set. Okay, so they are in one part.
Hey guys, if you are looking for help with learning discrete math or proofs, I know they're tough, then make sure to subscribe, as I'm literally going to be posting every example I have here for free on YouTube to help you learn and understand discrete math proofs. Back to the example.
What else? Let's look at the set 1. What else is in the partition set, or the partite set, that contains the set 1? Well, when I intersect 1 with B, I get 1. What else intersects with B to get 1? Well, again, if it contains 2, it would contain 2, so that's no good. But can it contain 3? Sure it can. 1 and 3 intersect with 1 and 2, give me the set 1. So that is the same intersection. And now we're starting to see the pattern. I can take any set to start with, 2, the intersection will be 2, and then the set that goes with it will be 2 and 3 will go together. Now, have I gotten all the sets? Well, remember my set is the set power set of A. A has 3 elements. The number of elements in the power set is 2 to the power of 3, which is 8. So I've got 2, 4, 6 here. I'm still missing 2 sets. So which 2 sets are they? Well, for instance, 1, 2, 3 is not there. So let's look at that one. 1, 2, 3. If I intersect that with B, I get 1, 2. Oh, none of these intersect with B to get 1, 2, and 1, 2 is the other missing set. There it is. Okay, so that's all the sets now, and I've written them in their partite sets here. So what I might do is do something like this. Let's say X1 is a set of empty set and the set 3. X2 is the set of the set 1 and the set 1, 3. X3 is the set of the set 2 and the set 2, 3. And lastly, X4 is the set of the set 1, 2, 3 and the set 1, 2. And those are the parts of the partition, and those form the partition. Is the partition induced by R? Great question. All right. Next here. Now A is bigger. A is a set 1, 2, 3, 4, 5, and B is a set 1, 2, 3. Find the equivalent class of X if X is the set 1, 3, 5. the equivalence class of 1 through 5. That is everything that intersects with B and gets the same thing as 1 through 5 intersects with B. So first off, what is the intersection of 1 through 5 with B? Well, 1 is in B, so it's 1. 3 is in B, so it's 3. And 5 is not. So it's 1, 3. And so what I'm looking for is everything in X that when I intersect it with B gives me the set 1, 3. Okay, well, what's in there? Certainly, 1 through 5 is in there. X is always contained in its own equivalence class, right? What else is in there? Anything that intersects with 1, 2, 3 and gives me 1, 3. So in other words, it must contain 1, it must contain 3, and it can't contain 2. And that's the only restrictions. It must contain 1, it must contain 3, and it cannot contain 2. Well, 1, 3 would work there, certainly. It must contain 1, must contain 3, cannot contain 2, and I've already got includes 5, I've got includes nothing. Well, I can include 4. And don't forget, I can include 4 and 5. And I think that's it. Must include 1, must include 3, can't include 2. So there's only one option for each of 1, 2, and 3. 4 and 5, 4, there are 2 options there, in the set or out the set. 5, there's 2 options there, in the set or out the set. So we have 2 times 2 is 4. We should have 4 elements, and we do. So there you go. Lastly, for A is the set 1, 2, 3, 4, 5, and B is the set 1, 2, 3, how many equivalence classes are in the partition induced by R? Now this is interesting. I could just go ahead and find them all, right? But I bet you, yeah, from what we just did, I bet you we got a hint. So the question is, because A is the same, B is the same, how many equivalence classes are there? We found 1 right there, and there's 4 things in it. And those are all the things that contain 1, don't contain 2, and do contain 3. See how that works? Out of the elements of B, you have a yes, no on each of those entries. Do contain 1, don't contain 2, and do contain 3. So that would be, if I have this at set 1, 2, 3, it's yes, I do contain 1, no, I don't contain 2, and yes, I do contain 3. Well, what if I change that? What if I said yes, yes, no? In other words, I do contain 1, I do contain 2, but I don't contain 3. Well, now I'm looking at a different equivalence class. The things that intersect with 1, 2, 3, and the intersection is 1, 2. So what's in there? Well, 1, 2 is in there. 1, 2, 4 is in there. 1, 2, 5 is in there. And 1, 2, 4, 5 is in there. In the same way as we did above. And so what you start to see is that the number of equivalence relations is exactly the number of ways I can write yes, no for these 3 things. So how many are there? 2 to the power of 3. There's 8. What if I said no, no, no? In other words, the set of things that intersect with that to give me nothing. Well, the empty set's in there, and the set 4 is in there, and the set 5 is in there, and the set 4, 5 is in there. And in fact, I think what you get here is that every equivalence class will have the same number of elements. Yeah. Every equivalence class will start with the set itself, and then add in a 4, add in a 5, and then add in both 4 and 5. And that'll always be it. So yeah, there are exactly 2 to the 3 different equivalence classes here.
Hey, thanks for watching. Remember, what I've explained here is just a tiny, tiny example in the literally infinite space of problems there could be that you'd run into. So, if you're interested in really understanding this content, getting a good grade because you understand the content, go ahead and click the first link down below and book a free call with me, and let's talk about if I can actually help you do well in this course.